Okay, the topic of chapter 2 is vectors. So most of it should be review. You should have seen vectors in Physics 170. Hopefully you may have seen it in vector calculus. I'm not sure if it's calculus 4 or calculus 3, but if you haven't seen it, try check your calculus book, and in any case, go back to your Physics 170. So pretty much vectors can be drawn graphically by an arrow. The length usually represent the magnitude, and the arrow and that little pointy head represents the direction. So usually what we do is we choose a coordinate system of your choice, x and y, so that we can represent the direction by an angle. So there are pretty much three ways to represent a vector. The first way is to use the magnitude and the direction. So that's what we've just seen. The second method is to use the component notation. And the third method to write down mathematically a vector is to use the unit vector notation. We will be using the three of them, and this will be the foundation of the whole course. So please make sure that you have all those vectors under control. Before we start, let's go over a couple of properties. For any vector, A, you can always decompose this vector into n other vectors. So for the case of two vectors, I can start with vector B and then vector C. So I can write that A is equal to B plus C. Or I can decompose it in more than two. I can go vector A is equal to vector B plus vector C plus vector D plus vector E. You can choose as many vectors as you want. So A is equal to B plus C plus D plus E. You can use the cumulativity of those vectors. So if you are going to add two vectors, let's say B and C, you can either write, in the case where you have vector A is equal to vector B plus vector C, since vector commute under addition, you could write the same way, vector A is equal to vector C plus vector B. You can use the associativity rule. So if you have a vector which can be decomposed into three, say vector A is equal to vector B plus vector C plus vector D, you can write it as A is equal to B plus C plus D, or vector A is equal to vector B plus C plus D. It doesn't make any difference. You can use the same two rules with scalars. So if you have A plus B, which are scalars, times a vector A, you can use the same distributive rule as the one you know for scalars. You can multiply the first scalar by the vector, then add the second scalar times the same vector. So you end up with AA plus BA. Similarly, if you have a scalar that multiplies the sum of two vectors, A plus B, you can use the same technique, scalar A times the first vector plus the operator scalar A times the second vector. So you end up with AA plus AB. If you have a vector A, let's say in this direction, and you have another vector which has the exact same length, but the direction is opposite, then the relationship between vector A and vector B is the minus sign. This implies that the magnitude of A is the same as the magnitude of B, but the direction is opposite. And this is mathematically represented by the minus sign. Okay, so we've seen the first method, which was to represent a vector A as its magnitude, which we usually write under those two bars, or just like this, and the direction, which is usually represented by the angle. That's one way to represent a vector. You want to make sure that whenever you write a vector, you specify those two quantities, because if you only specify one, it doesn't characterize the vector entirety, so you need those two pieces of information. Second method, that's called the component notation. This requires a coordinate system. Technically, the first method also requires a coordinate system in order for you to define the angle theta, and you can choose whatever you want. So let's imagine you have a vector A. You would like to characterize it with the first method, so let's pick a coordinate system which we will center at the beginning of the vector. Let's call this x, and let's call this axis y. You can choose any coordinate system. It doesn't have to be perpendicular, it doesn't have to be orthonormal. For simplicity, we'll choose orthonormal, which means that x and y is perpendicular to each other, and the scale is the same on both axes. So if you do this, you can just take your ruler, measure the length of your vector, this will be your magnitude, and then the convention is to measure the angle from the positive axis going counterclockwise, and this will be your angle theta. Again, you don't have to respect that convention. If you don't like to do this, you can always measure, say, alpha from y going clockwise. But if you do this, you want to make sure that you specify it before you start the problem. If you don't specify it, I would assume that you will always measure the angle from the positive x-axis going counterclockwise. Now that's one way. You can use the component notation, and instead of using the angle and the magnitude, we will be using the projection of the vector onto the x-axis and into the y-axis, which will be either this one or that one. So really, the component notation is nothing different from decomposing a vector. We've seen that we could decompose a vector A as vector B, another vector C. The component notation will do the same thing, except they will choose vector B and C such that B and C are perpendicular to each other. And then we'll call B AX, because we will align this vector along the x-axis, and we'll call vector C AY, because it will have the direction of your other axis. And that's it. And mathematically, the way we write it is vector A is equal to vector AX plus vector AY. The third method is to use unit vectors. What we can do is take any vector A, which can have any length, write it in terms of the unit vector, which is another vector with the same direction as your vector A, but whose length is 1. So unit vector EA, which I write with a little hat, has a property that the magnitude is 1 all the time. Therefore, you can write your vector A as this little unit vector times the magnitude of your vector. For example, in this case, if you have to use 1 time, 2 time, and 3 times your unit vector EA, then A would be 3 EA, and the magnitude A is 3. Now we can use this definition and go back to our component notation and rewrite both component AX and AY under this form. The convention is to use, when you pick a coordinate system X and Y, is to use I for the unit vector in the X direction and J as the unit vector in the Y direction. Therefore, when you want to express your vector A, and you project it on both axes, this is vector AX, this is vector AY, you can write vector AX as magnitude of A times I. Actually, you want to take the component, the X component of the magnitude. And for the Y, AY will be magnitude AY times J. So magnitude AX is the distance from here to here. Magnitude AY is the distance from here to here. Therefore, you can rewrite your vector A as AXI excuse me, plus AYJ. That's the standard way of writing vectors in component notation. Now let's imagine that you're given a vector in terms of its magnitude A and its angle, and you would like to write it in component notation. All you have to do is figure out AX and AY, but we can do that easily using Pythagoras theorem. If you redraw your little vector in your coordinate system, you will see easily that this length and this length create a right triangle. This is AY, this is AX, this is your angle theta, and this is your magnitude A. Therefore, if you know A and theta, you can deduce AY and AX using the sine and the cosine. So AY is defined as A sine theta, AX is defined as A cosine theta. You've used what you know, the magnitude and the angle, and you can deduce the component. So if you start with a vector given to you with its magnitude and its angle, you can use this relationship to express the x component of the vector and the y component of the vector, and therefore then you can write the vector A as AXI plus AYJ, while you would just plug A sine theta in AY, A cosine theta in x, and that's it. Now if you want to go the other way, let's say you start with this. Now you have to figure out A and theta from the AX and the AY component. You can use again the same theorem. Going back to our triangle, we know that magnitude A squared is equal to magnitude AY squared plus magnitude AX squared. You add them up, the square root, and you got A. Therefore A is equal to AX squared plus AY squared. So if you know this and this, you can deduce magnitude A. Similarly, for the angle, you can go back to those two equations, 1 and 2. take 1 divided by 2. The magnitude will cancel out. And you end up with a relationship that AY over AX is tangent of the angle. Therefore, if you're looking for the angle starting from AX and AY, all you have to do is take the arctangent of the Y component divided by the X component. Okay, so that should be all review. The third one, let's go back to our unit vector. We've seen that you can express a vector A as magnitude of A times unit vector EA. So let's imagine that you know this vector and you would like to figure out what is unit vector. You know that the magnitude is 1. This you always know. And you know that the direction of EA must be the same as the direction of A. So all you have to do is take your vector divided by its magnitude and you got unit vector. So let's do an example. Let's imagine you have a vector A given as magnitude of A is 10 and theta is 45, and you would like to express A in component notation, which is AXI plus AYJ. AX by definition is the magnitude of the vector A times cosine of the angle. AY is the magnitude of A times the sine of the angle. If you plug everybody in, oops, that must be 45, that should be 45, A is equal to 10, so you get 10 times square root of 2 over 2, 10 square root of 2 over 2. You have to be careful. This definition, AX is equal to A cosine alpha and AY is equal to A sin alpha, is true only if you respect the convention that you measure the angle from the positive x going counterclockwise. If you define your angle any other ways, you can use that shortcut. Now let's try to express vector A in terms of its magnitude and its unit vector. The magnitude is given to us, it's 10. We need to know vector A, we just figure it out. So from the previous question we can write that A is equal to 5 square root of 2 times I plus 5 square root of 2 times J. That's your vector in component notation. And if you want to figure out the unit vector, you take this vector and you divide it again by its magnitude, which is 1 over 10, 5 square root of 2i plus 5 square root of 2j. And you end up with unit vector of A is equal to square root of 2 over 2 I plus square root of 2 over 2j. And you should be able to verify that if you take the magnitude of this, you should get 1. So you can always check. If you square both terms and add them up and take the square root, you should end up with 2/4 plus 2/4 square root. That should give you 4/4, which is 1, so it's all good. Okay, so the main idea is when you write a vector A, this is a vector. It has a little arrow on the top. If you want to write this vector equal to something else, this needs to be a vector. So this doesn't make any sense. This is a scalar, so it won't work. you need to make sure that you express your vector in terms of the sum of other vectors. And the idea is to use those unit vectors for component notation. Or a unit vector which is a line along this vector A in the right hand side. So on both sides you got both vectors. So that mathematically it's correct.